If you step outside tonight, away from the glow of city lights, and let your eyes adjust to the darkness for 20 minutes or so, you might notice something remarkable in the constellation that shares its name with an ancient princess from Greek mythology. There, hanging in the velvet blackness of space, sits a faint smudge of light. It looks almost like a tiny cloud, perhaps a wisp of cosmic mist that wandered too far from the bright band of the Milky Way stretching overhead. Most people glance right past it without a second thought, but that pale, elongated glow is not a cloud at all. It is the Andromeda Galaxy, and it represents one of the most profound sights available to the unaided human eye. What you are seeing when you gaze upon that distant smear is the combined light of approximately 1 trillion stars, gathered together in a vast rotating spiral roughly 220,000 light-years across. Each photon striking your retina has traveled through the emptiness of intergalactic space for approximately 2.5 million years to reach you. When that light first departed Andromeda, our distant ancestors were just beginning to experiment with primitive stone tools on the African savanna. Homo erectus had not yet learned to control fire. The entire arc of human civilization, every empire that rose and fell, every war fought, every poem written, every child born, and every elder laid to rest, all of it unfolded during the time it took that ancient light to cross the void between galaxies. And yet, despite this incomprehensible distance, Andromeda remains the most distant object you can see without the aid of a telescope or binoculars. But here is something that transforms that serene celestial vision into something far more dramatic. That beautiful spiral galaxy is not simply hanging motionless in the cosmic darkness, it is moving. More specifically, it is falling toward us. Right now, at this very moment as you read these words, Andromeda is hurtling through intergalactic space in our direction at approximately 110 kilometers per second. That translates to roughly 250,000 miles per hour, a velocity so tremendous that it defies everyday comprehension. If you could somehow travel at that speed here on Earth, you would circle the entire planet in under 6 minutes. You would reach the moon in less than an hour. Some recent studies using data from the Gaia Space Telescope suggest the disk might extend even farther, perhaps up to 200,000 light-years when you include the faint outer regions where stellar density drops to nearly nothing. But the bulk of the visible galaxy, the bright portion containing most of the stars, spans that central figure of roughly 90,000 light-years. Despite this enormous diameter, the disk is remarkably thin. At the location of our solar system, the disk is only about 1,000 light-years thick, though it puffs up somewhat toward the center and thins out toward the edges. If you could shrink the Milky Way down to the size of a dinner plate, the disk would be thinner than a sheet of paper. This extreme flatness results from the galaxy's rotation. Just as a spinning ball of pizza dough flattens into a disk, the rotation of the Milky Way over billions of years has concentrated most of its matter into a thin plane. How many stars does this vast disk contain? The honest answer is that we do not know precisely, and estimates vary considerably depending on the assumptions astronomers make about the population of dim, low-mass stars that are difficult to detect. Current estimates suggest somewhere between 100 billion and 400 billion stars call the Milky Way home. That enormous range reflects our uncertainty about the faint end of the stellar population. The most common stars in the universe are red dwarfs, dim objects with less than half the mass of our sun that burn so coolly they glow a deep crimson. These stars are so faint that we can only detect them when they are relatively nearby, within a few hundred light years. Extrapolating their numbers across the entire galaxy introduces substantial uncertainty. For comparison, consider that if the Milky Way contains 300 billion stars and you tried to count them at a rate of 1 per second, it would take you nearly 10,000 years to finish the count, assuming you never slept and never took a break. The sheer number of stars in our galaxy defies human intuition. And yet, as impressive as that number sounds, it pales compared to Andromeda's trillion-star population. Our approaching neighbor contains somewhere between 2 and 3 times as many stars as we do, a difference that will have significant implications when the two galaxies finally merge. The stars of the Milky Way are not distributed uniformly throughout the disk. Instead, they concentrate along spiral arms that wind outward from the galactic center, creating the characteristic pinwheel appearance that gives spiral galaxies their name. Our galaxy possesses 2 major spiral arms and several smaller arm segments, or spurs. The major arms are named after the constellations toward which we observe them from Earth, the Perseus arm and the Scutum Centaurus arm. These arms are not solid structures like the spokes of a wheel. Stars do not remain permanently attached to a particular arm. Instead, the arms are density waves, regions where gas and stars are temporarily compressed as they orbit the galactic center. Think of traffic on a highway. When cars slow down for construction or an accident, they bunch together, creating a region of higher density that persists even as individual cars pass through it and continue on their way. The spiral arms work similarly. Stars and gas clouds move through the arms, experiencing a temporary compression before continuing their orbital journey. This compression is precisely what makes spiral arms visible. When gas clouds are squeezed by the density wave, they collapse more readily to form new stars. The brightest, hottest, and most massive of these newborn stars blaze with intense blue-white light, illuminating the arms and making them stand out against the older stellar population. These massive stars live fast and die young, exhausting their nuclear fuel in just a few million years before exploding as supernovae. Consequently, they never travel far from their birthplace before dying, which is why bright blue stars trace the spiral structure so clearly. Our own solar system resides in a relatively minor structure called the Orion Arm, sometimes referred to as the local arm or the Orion Spur. This arm segment lies between the larger Perseus and Sagittarius arms, and it is named for the constellation Orion, whose bright stars, including the famous Hunter's Belt and the red supergiant Betelgeuse, all belong to this local structure. The Orion Arm stretches approximately 10,000 light-years in length and about 3,500 light-years in width, making it a modest feature by galactic standards. Our position within the Orion Arm places us roughly 26,000 light-years from the galactic center, stars. Surrounding this bulge, a flattened disk extends outward, crossed by dark lanes of dust that absorb and obscure the light of stars behind them. Within this disk, spiral arms wind gracefully outward, studded with bright blue regions where young, hot stars have recently formed from collapsing gas clouds. The overall impression is one of stately grandeur, a cosmic pinwheel rotating slowly through the darkness over timescales that dwarf human comprehension. How many stars does Andromeda contain? Estimates have varied considerably over the years as our observational techniques have improved, but current measurements suggest approximately 1 trillion stars, possibly more. This number exceeds the Milky Way's stellar population by a factor of somewhere between 2 and 3, depending on which estimates you use for both galaxies. 1 trillion is a number that resists intuitive understanding. If you attempted to count Andromeda's stars at a rate of 1 per second, it would take you over 31,000 years to complete the task, never pausing to sleep or eat or rest. Every single star in that vast assemblage is a sun in its own right, many of them accompanied by planets, some of those planets potentially harboring conditions suitable for life as we understand it. The trillion stars of Andromeda represent a range of stellar types spanning the full diversity of the cosmos. Red dwarfs, those dim, long-lived embers that constitute the majority of all stars, make up the bulk of the population. Sun-like yellow stars burn steadily through their hydrogen fuel over billions of years. Massive blue giants blaze with furious intensity, burning through their nuclear reserves in mere millions of years before dying in spectacular supernova explosions. Ancient red giants, swollen to enormous size as they exhaust the hydrogen in their cores, glow with ruddy light in the later stages of stellar life. White dwarfs, the dense remnants of stars like our Sun, slowly cool over billions of years, gradually fading from view. Neutron stars, the collapsed cores of massive stars that died in supernovae spin rapidly and emit beams of radiation that sweep across space like cosmic lighthouses. And scattered among this stellar menagerie are black holes of various sizes, the gravitational tombstones of the most massive stars. At the very heart of Andromeda, concealed within the bright glow of the central bulge, lurks something far more massive than any stellar mass black hole. Andromeda possesses its own supermassive black hole, a gravitational monster that dwarfs Sagittarius A star by a substantial margin. Estimates of its mass have varied as measurement techniques have improved, but current values place it somewhere between 100 million and 140 million times the mass of our Sun. This makes Andromeda's central black hole roughly 25 to 35 times more massive than the one at the center of our own galaxy. Consider what this means. If Sagittarius A star, with its 4 million solar masses, were placed in our solar system, its event horizon would fit inside Mercury's orbit. Andromeda's black hole, with its 100 million plus solar masses, would have an event horizon extending outward to roughly 400 million kilometers from the center, reaching past the orbit of Mars. When these two supermassive black holes eventually encounter each other during the galactic merger, the gravitational dynamics will be dominated by Andromeda's far more massive central object. The dance of the black holes will be led by the larger partner. Why does Andromeda's black hole so significantly outweigh our own? The answer likely relates to the different evolutionary histories of the two galaxies. Supermassive black holes grow by consuming gas, dust, and occasionally stars that wander too close to the galactic center. They also grow through mergers with other black holes when their host galaxies collide and combine. Andromeda's larger black hole suggests a more active feeding history, perhaps driven by more numerous or more gas-rich mergers over the course of its 13 billion-year existence. The galaxy's greater overall size and mass would have made it more effective at capturing and consuming smaller satellite galaxies, each potentially contributing material to the growing central black hole. Despite its greater mass, Andromeda's supermassive black hole appears to be relatively quiescent at the present time, not actively consuming large quantities of material and therefore not producing the brilliant radiation that characterizes actively feeding black holes known as quasars or active galactic nuclei. The same is true of Sagittarius A star in our own galaxy. Both black holes are essentially dormant, occasionally snacking on a passing gas cloud or unfortunate star, but not engaged in the sustained feeding frenzy that can make a galactic center outshine all the stars in its host galaxy combined. This could change during the merger, when gravitational interactions might funnel fresh supplies of gas toward one or both central black holes, potentially reigniting them into brief but spectacular activity. The distance separating us from Andromeda deserves careful consideration, for it provides essential context for understanding both the scale of the approaching collision and the time required for it to unfold. Andromeda lies approximately 2.5 million light-years from our solar system. A light-year, the distance light travels in 1 year, moving at roughly 300,000 kilometers per second, works out to approximately 9.5 trillion kilometers. Multiply that by 2.5 million, and you arrive at a distance of roughly 24 quintillion kilometers, a number so vast it becomes essentially meaningless in everyday terms. Perhaps a more intuitive way to appreciate this distance is to consider travel times. Light, the fastest thing in the universe, requires 2.5 million years to make the journey from Andromeda to Earth. The photons striking your eye when you observe that faint smudge in the autumn sky departed Andromeda when our ancestors were still learning to chip stone tools. If you could somehow travel at the speed of the fastest spacecraft humanity has ever launched, the Helios 2 solar probe, which reached speeds of about 250,000 kilometers per hour, the trip to Andromeda would require roughly 11 billion years, nearly the current age of the universe. Even at the tremendous velocity of 110 kilometers per second at which Andromeda approaches us, the journey from there to here requires several billion years to complete. And yet, despite this incomprehensible separation, Andromeda is our neighbor in the cosmic sense. It is the nearest large spiral galaxy to the Milky Way, the dominant member of our local cosmic community. Beyond Andromeda, the next comparable spiral galaxies lie tens of millions of light-years distant, separated from us by gulfs of emptiness that make the Milky Way-Andromeda gap seem almost cozy by comparison. In the vast loneliness of intergalactic space, Andromeda is practically next door. Like our own Milky Way, Andromeda does not travel through the cosmos alone. It is accompanied by a retinue of smaller satellite galaxies, gravitationally bound companions that orbit the larger spiral-like moons around a planet. Astronomers have identified at least 14 satellite galaxies associated with Andromeda Miss. The breakthrough came from the Hubble Space Telescope and a team of astronomers led by Roland Vandermarle of the Space Telescope Science Institute in Baltimore, Maryland. Vandermarle and his colleagues realized that while measuring the motion of Andromeda as a whole remained extraordinarily difficult, they could potentially achieve the necessary precision by focusing on individual regions within the galaxy and measuring their motion relative to extremely distant background objects. The approach was conceptually straightforward but technically demanding. The team selected several fields within Andromeda and imaged them repeatedly over a span of 5 to 7 years. By comparing images taken years apart, they could look for tiny shifts in the positions of stars within Andromeda relative to much more distant galaxies lying far behind. These background galaxies, billions of light-years away, are so remote that their own motions across the sky are completely negligible. They serve as fixed reference points against which the motion of closer objects can be measured. The technical challenges involved were formidable. The expected motion, remember, was on the order of millionths of an arc-second per year. The pixel scale of the Hubble Space Telescope's cameras is roughly 50 milliarc-seconds per pixel, meaning the expected annual motion was roughly 1/10,000th of a pixel. Detecting such minuscule shifts required extraordinarily precise image processing, careful accounting for every source of measurement error, and years of patience as the baseline between observations grew. Vandermarle's team observed 3 separate fields within Andromeda using Hubble's Advanced Camera for Surveys and Wide Field Camera 3. They tracked the positions of thousands of individual stars within the galaxy, measuring how each star moved relative to the background galaxies over the observation period. Then, they combined all these measurements, averaging out the random motions of individual stars within Andromeda, which orbit the galactic center and therefore move in various directions, to extract the systematic motion of the galaxy as a whole. The results, announced in 2012 after years of data collection and analysis, were conclusive. Andromeda's transverse velocity is approximately 17 kilometers per second, far less than its approach velocity of 110 kilometers per second. The numbers told an unmistakable story. Andromeda is heading almost directly toward us. Its sideways motion is too small to cause a miss. The 2 galaxies are on a collision course, and the impact is essentially inevitable. To visualize what these velocities mean, imagine the motion of Andromeda as an arrow. The arrow points mostly toward us, representing the approach velocity measured by Slipher a century ago. But the arrow is tilted slightly to the side, representing the small transverse component measured by Vandermarle. The tilt is so slight that the arrow still points almost directly at our position. Andromeda is not going to sail past, it is going to hit. The precision of Vandermarle's measurement is worth appreciating. The team determined Andromeda's transverse velocity with an uncertainty of roughly plus or minus 34 kilometers per second. Even taking this uncertainty into account, the range of possible transverse velocities is still small compared to the approach velocity. The probability of a direct collision, rather than a glancing blow or a miss, is very high. The simulation work that accompanied the observational paper, using computer models to project the future trajectories of the Milky Way, Andromeda, and the smaller Triangulum galaxy over billions of years, consistently produced collision scenarios. The galaxies meet, interact, separate briefly, then fall back together and merge. The final result, some 6 or 7 billion years from now, is a single combined galaxy where 2 spiral systems once existed. Following the Hubble observations, additional data arrived from another revolutionary space mission, the Gaia spacecraft. Launched by the European Space Agency in 2013, Gaia was designed to create the most precise three-dimensional. The interaction is a simple two-body problem. The research team recognized that the local group is a complex dynamical system containing multiple massive objects whose gravitational influences cannot be ignored. They incorporated not just the Milky Way and Andromeda, but also the Large Magellanic Cloud and the Triangulum Galaxy, the third and fourth most massive galaxies in our cosmic neighborhood. And rather than running a single simulation or a handful of scenarios, they employed Monte Carlo methods to explore 100,000 different possible futures, each one starting from slightly different initial conditions within the range of our observational uncertainties. 100,000 simulations. Think about what that number represents. Each simulation tracked the gravitational interactions of 4 massive galaxies over 10 billion years of simulated time, calculating how gravitational forces would alter trajectories, how orbits would evolve, how close encounters would deflect motion. The researchers varied the initial positions and velocities of each galaxy within the ranges allowed by our measurements, recognizing that even small uncertainties in current observations can compound into dramatically different outcomes over billions of years. The result was not a single prediction, but a probability distribution, a statistical map of possible futures weighted by their likelihood. What the simulations revealed was startling. The near-certain collision that had been proclaimed since 2012 turned out to rest on incomplete analysis. When the gravitational influence of the Large Magellanic Cloud was properly accounted for, the probability of a direct Milky Way-Andromeda collision within the next 4 to 5 billion years dropped dramatically. Instead of the essentially 100% certainty that previous studies had suggested, the new analysis found only about a 2% chance of a head-on collision in that traditional time frame. The famous 4 billion year deadline, it turned out, was probably wrong. But if a near-term collision is unlikely, what does the future hold? The simulations revealed a range of possibilities. In roughly half of the scenarios, the Milky Way and Andromeda do eventually merge, but on a much longer timescale than previously believed. Instead of colliding while our sun is transforming into a red giant, the galaxies might not come together until more than 10 billion years from now, long after our sun has faded to a cooling white dwarf. In the other half of scenarios, the galaxies avoid collision entirely for the duration of the simulation, remaining on separate but interacting orbits around each other for at least 10 billion years into the future. How can the addition of one satellite galaxy make such a dramatic difference to predictions about an event involving 2 much larger systems? The answer lies in the geometry of the Large Magellanic Cloud's orbit and a phenomenon that might be called gravitational perturbation. The Large Magellanic Cloud is not a trivial object. It is a substantial galaxy in its own right, spanning roughly 32,000 light-years and containing approximately 20 billion stars. While this makes it far smaller than either the Milky Way or Andromeda, it is still the 4th most massive galaxy in the local group, outweighing all but the 2 dominant spirals and the Triangulum Galaxy. And crucially, recent observations have revised our estimates of its mass upward. The Large Magellanic Cloud may be significantly more massive than astronomers believed even a decade ago, perhaps as much as 1/10 or even 1/5 the mass of the Milky Way itself. A more massive satellite exerts a stronger gravitational pull on its host galaxy. The geometry of the situation is what makes this gravitational pull so consequential. The Large Magellanic Cloud orbits the Milky Way on a trajectory that is roughly perpendicular to the plane containing the Milky Way and Andromeda. Imagine the Milky Way and Andromeda approaching each other along a relatively flat path, like 2 cars driving toward each other on a highway. Now, imagine a heavy weight attached to one of those cars by a rope, swinging in a circle above and below the car rather than alongside it. As the weight swings, it pulls the car slightly upward, then slightly downward, altering its trajectory in ways that a driver looking only at the road ahead might not anticipate. The Large Magellanic Cloud plays a similar role in the cosmic dance between the Milky Way and Andromeda. As it orbits our galaxy on its perpendicular path, it exerts a gravitational tug that pulls the Milky Way slightly out of the plane it would otherwise follow. This displacement might seem small, but over billions of years, even small deflections can compound into significant trajectory changes. The simulations suggest that in many scenarios, this gentle tug from the Large Magellanic Cloud is sufficient to cause Andromeda to miss the Milky Way entirely, passing by at a distance of roughly 500,000 light-years rather than plowing directly through. 500,000 light-years is still a relatively close approach by galactic standards. The current separation between the Milky Way and Andromeda is approximately 2.5 million light-years, so a close pass at 500,000 light-years would bring the galaxies 5 times closer together than they are today. At such distances, gravitational tidal effects would become significant. Both galaxies would experience substantial distortion, with their outer regions stretched and deformed by the gravitational pull of the other. Stars in the outer halos might be stripped away, transferred from one galaxy to the other, or flung out into intergalactic space. The spiral structures of both galaxies would likely be disrupted, though not necessarily destroyed. But a close pass is not a merger. If the galaxies miss each other on their first approach, what happens next? The simulations show that the story does not end with a single flyby. After their close passage, the Milky Way and Andromeda would swing around and approach each other again, drawn back together by their mutual gravitational attraction. This second approach might result in a merger, or it might lead to another close pass, with the process repeating over billions of years. The gravitational dance would continue until either the galaxies finally collide and merge, or until they settle into some kind of stable binary orbit around their common center of mass. The second major player that the new simulations incorporated is the Triangulum Galaxy, also known as Messier 33. Triangulum is the third largest galaxy in the local group, roughly twice the size of the Large Magellanic Cloud, but still substantially smaller than either the Milky Way or Andromeda. It is a satellite of Andromeda, orbiting the larger spiral in much the same way that the Magellanic Clouds orbit our own galaxy. But satellite status does not mean Triangulum is gravitationally insignificant. Its mass is sufficient to influence the dynamics of the entire local group system. The simulations revealed an interesting possibility regarding Triangulum's future. In approximately 86% of scenarios, Triangulum collides with Andromeda before either spiral encounters the Milky Way. This makes intuitive sense given Triangulum's status as an Andromeda satellite. It is gravitationally bound to the larger galaxy and orbits relatively close to it. If that collision occurs first, Andromeda would grow slightly larger and more massive, potentially affecting the eventual dynamics of any subsequent interaction with the Milky Way. Similarly, the simulations suggest that the Milky Way will almost certainly merge with the Large Magellanic Cloud before any collision with Andromeda occurs. The Large Magellanic Cloud is already in a declining orbit around our galaxy, gradually spiraling inward due to dynamical friction, the same process that causes supermassive black holes to sink toward the centers of merged galaxies. Current estimates suggest this merger could occur within 2 to 3 billion years, well before any potential encounter with Andromeda. When it happens, the Large Magellanic Cloud will be absorbed into the Milky Way, adding its 20 billion stars to our galaxy's stellar population, and potentially triggering a modest burst of new star formation as gas clouds collide and compress. What emerges from these simulations is a picture of the local group's future that is far more complex and uncertain than the simple collision narrative that dominated for over a decade. Instead of a single dramatic event 4 billion years hence, we may be facing a series of smaller mergers unfolding over tens of billions of years. The Milky Way absorbs the Large Magellanic Cloud. Andromeda absorbs Triangulum. Then, eventually, the two resulting galaxies come together, though the timing of that final union remains highly uncertain. Some scenarios in the simulation showed particularly intriguing outcomes. In a small percentage of cases, the gravitational interactions among the four major local group galaxies became complex enough that one or more galaxies were ejected from the system entirely, sent hurtling off into the cosmic void as a result of multi-body gravitational interactions. While these scenarios are unlikely, they illustrate the fundamental unpredictability of gravitational dynamics when multiple massive objects are involved. What should we make of this dramatic revision to what was once considered settled science? The first lesson is one of epistemic humility. The 2012 prediction of an inevitable collision was. The second lesson concerns the nature of uncertainty in science. When scientists reported that Andromeda would collide with the Milky Way in 4 billion years, they were not lying or exaggerating. They were conveying the results of their analysis, wait longer than we once thought. But the story of scientific understanding is rarely about practical implications. It is about the quest to comprehend our place in the cosmos, to understand the forces that shape our universe, and to grapple honestly with the limits of our knowledge. The 2025 revision to the Milky Way-Andromeda collision prediction is a beautiful example of science working as it should, with new data and better methods leading to revised understanding, and with scientists openly acknowledging the uncertainties that remain. The galaxies will do what they will do, regardless of our predictions. Gravity will continue to pull the Milky Way and Andromeda toward each other, modified by the subtle influences of the Large Magellanic Cloud and Triangulum and all the other objects in the local group. The cosmic dance will unfold over timescales that render human civilization a mere eye blink in the vast sweep of galactic evolution. And whether that dance leads to collision in 4 billion years or 10 billion years or longer, it will be magnificent to witness for whatever observers are present to see it. To fully understand the story of the Milky Way and Andromeda, we need to zoom out and consider the larger cosmic context in which these two giant spirals exist. They are not alone in the universe, drifting through an empty void with only each other for company. Instead, they anchor opposite ends of a gravitationally bound collection of galaxies that astronomers call the local group. This cosmic neighborhood, our home cluster in the vast architecture of the universe, contains the stage upon which the drama of the approaching merger will unfold. The local group is a modest galaxy cluster by cosmic standards, containing approximately 80 known member galaxies spread across a region roughly 10 million light-years in diameter. Most of these members are small dwarf galaxies, containing only millions or billions of stars rather than the hundreds of billions found in the major spirals. But even these small galaxies contribute to the gravitational dynamics of the group and the total mass of the local group, including all the dark matter that pervades the system, amounts to somewhere between 1 and 2 trillion times the mass of our Sun. The structure of the local group resembles a dumbbell or barbell, with two distinct concentrations of mass connected by a relatively sparse bridge. On one end of the dumbbell sits the Milky Way, surrounded by its retinue of satellite galaxies. On the other end sits Andromeda, accompanied by its own collection of gravitational companions. These two lobes dominate the group, containing the vast majority of its mass and determining the overall gravitational dynamics that govern the motions of all the smaller members. Between the two major lobes, the density of galaxies drops considerably, though this intergroup space is not entirely empty. A few small dwarf galaxies inhabit this region, some of them apparently not gravitationally bound to either of the major spirals, but instead moving independently through the local group. These isolated dwarfs represent the most vulnerable members of the group, potentially subject to capture by one or the other major spiral, or perhaps destined to remain independent for billions of years before eventually falling into the merged remnant of the Milky Way-Andromeda collision. The third largest member of the local group, after the two dominant spirals, is the Triangulum Galaxy, also known as Messier 33 or simply M33. Triangulum is a spiral galaxy in its own right, though substantially smaller than either the Milky Way or Andromeda. It spans roughly 60,000 light-years in diameter and contains somewhere between 30 and 40 billion stars, perhaps 1/10 the stellar population of our own galaxy. Despite its smaller size, Triangulum displays beautiful spiral structure with distinct arms winding outward from a relatively modest central bulge. Triangulum lies approximately 3 million light-years from the Milky Way and roughly 750,000 light-years from Andromeda, making it a relatively close companion to the larger spiral. For many years, astronomers debated whether Triangulum was gravitationally bound to Andromeda, or whether it merely happened to be passing through the same region of space. Recent observations and dynamical modeling suggest that Triangulum is indeed a satellite of Andromeda, orbiting the larger galaxy on a trajectory that will eventually bring the two spirals into close interaction or direct collision. The fate of Triangulum is intertwined with the larger story of the Milky Way-Andromeda merger. As we discussed in the previous section, simulations suggest an 86% probability that Triangulum will collide with Andromeda before any encounter between Andromeda and the Milky Way occurs. If this happens, Andromeda will grow slightly larger and more massive, potentially affecting the eventual dynamics of its interaction with our galaxy. Alternatively, in some scenarios, Triangulum survives long enough to participate in the three-way merger, adding its tens of billions of stars to the combined remnant. Below these three major spirals in the local group hierarchy comes the Large Magellanic Cloud, the fourth most massive member of our cosmic neighborhood. The Large Magellanic Cloud is visible from the southern hemisphere as a conspicuous patch of light near the constellation Dorado, easily mistaken for a detached piece of the Milky Way by casual observers. It lies approximately 163,000 light-years from our galaxy, close enough that the two systems are clearly gravitationally interacting. The Large Magellanic Cloud spans roughly 32,000 light-years and contains approximately 20 billion stars, making it substantial enough to exert significant gravitational influence on its surroundings. For centuries, astronomers classified it as an irregular galaxy, lacking the organized spiral or elliptical structure seen in larger galaxies. More recent observations have revealed hints of a bar and spiral arm structure, suggesting the Large Magellanic Cloud may be a barred spiral galaxy that has been distorted by its gravitational interactions with the Milky Way. The Small Magellanic Cloud, a companion to the Large Magellanic Cloud, lies somewhat farther from us at approximately 200,000 light-years distance. It is considerably smaller than its larger sibling, spanning only about 7,000 light-years and containing several hundred million stars. The two Magellanic Clouds are gravitationally bound to each other, as well as to the Milky Way, forming a triple system that orbits our galaxy together. Evidence suggests that the Small Magellanic Cloud may eventually be consumed by the Large Magellanic Cloud before both are absorbed into the Milky Way. Connecting the two Magellanic Clouds is a remarkable structure called the Magellanic Stream, a long ribbon of hydrogen gas that stretches across more than 100 degrees of sky when viewed from Earth. This stream represents material that has been tidally stripped from the Magellanic Clouds by the gravitational pull of the Milky Way. Its existence demonstrates that galactic interactions and mergers are not just future events, but ongoing processes that we can observe happening in real time if we consider timescales of millions of years. The Milky Way's satellite system extends well beyond the Magellanic Clouds. Astronomers have identified approximately 60 satellite galaxies orbiting our galaxy, with new discoveries being made regularly as survey telescopes probe ever fainter magnitudes. Most of these satellites are dwarf spheroidal galaxies, small, roughly spherical collections of old stars with little or no gas for ongoing star formation. They include objects like the Sagittarius Dwarf Elliptical Galaxy, which is currently being torn apart by the Milky Way's tidal forces, and the Draco and Ursa Minor dwarfs, which orbit at great distances from our galactic center. The Sagittarius Dwarf deserves particular mention because it demonstrates what happens to smaller galaxies that venture too close to larger ones. Discovered in 1994, the Sagittarius Dwarf is located on the far side of the Milky Way's center, as seen from Earth, approximately 70,000 light-years from our position. It is in the process of being absorbed by our galaxy, stretched and shredded by tidal forces into long waves breaking against rocks. These mental pictures, while vivid, fundamentally mislead us about what actually happens when galaxies meet. A galaxy collision is unlike any collision humans have ever witnessed or could ever witness on human scales. To understand what will actually happen when these two island universes come together, we need to grasp some counterintuitive physics and appreciate just how much empty space galaxies contain. Consider first the scale of a typical star compared to the distances between stars. Our Sun has a diameter of roughly 1.4 million kilometers, an enormous object by human standards. Yet the nearest star to the Sun, Proxima Centauri, lies over 4 light-years away, which translates to approximately. The antennae have been interacting for several hundred million years and provide a preview of what the Milky Way and Andromeda might look like during certain phases of their merger. While stars rarely collide during galaxy mergers, the same cannot be said for gas. Unlike stars, which are compact objects separated by vast distances, interstellar gas is spread diffusely throughout a galaxy, forming thin clouds that extend across enormous volumes. When two galaxies merge, their gas clouds can and do collide directly. These collisions compress the gas, heating it to high temperatures and triggering shock waves that propagate through both galaxies. The collision of gas clouds has profound consequences for the merged galaxy. Compressed gas tends to collapse under its own gravity, fragmenting into dense clumps that eventually form new stars. This is why galaxy mergers often trigger intense bursts of star formation, creating spectacular stellar nurseries throughout the merged system. The starburst phenomenon, which we will explore in greater detail later, is one of the most dramatic effects of galaxy collisions and fundamentally alters the stellar population of the merged galaxy. Any discussion of galaxy collision physics would be incomplete without addressing dark matter, the mysterious substance that dominates the mass budget of galaxies. Dark matter does not emit, absorb, or reflect light, making it invisible to telescopes that observe electromagnetic radiation. Yet, it exerts gravitational force, and through careful measurements of stellar motions and gravitational lensing, astronomers have determined that dark matter constitutes roughly 85% of all matter in the universe. Each galaxy is embedded within a vast halo of dark matter that extends far beyond the visible disk of stars. The Milky Way's dark matter halo likely extends roughly 2 million light-years from the galactic center, far larger than the stellar disk, which spans only about 100,000 light-years. Andromeda's dark matter halo is similarly extensive. When two galaxies merge, their dark matter halos merge as well. And because dark matter dominates the total mass, it largely determines the gravitational dynamics of the collision. Dark matter particles, whatever they are, interact only through gravity, not through electromagnetic forces or the strong nuclear force. This means dark matter cannot collide in the traditional sense. When two dark matter halos meet, the particles pass through each other just as stars do, interacting only gravitationally. However, because dark matter is distributed much more smoothly than stars, the gravitational effects are more like a fluid mixing than discrete particles scattering. The two dark matter halos gradually interpenetrate and blend, forming a single combined halo that encompasses the merged stellar system. The presence of dark matter affects every aspect of the merger process. It determines the initial approach velocity of the two galaxies, as the gravitational pull depends on total mass, including dark matter. It influences the tidal forces experienced by each galaxy, since these forces depend on the mass distribution. It governs the rate at which the two galactic cores spiral together after the initial passage through a process called dynamical friction, and it shapes the final structure of the merged galaxy, determining how the stars distribute themselves within the combined gravitational potential. Dynamical friction deserves special attention because it explains how galaxy mergers actually complete. After two galaxies pass through each other, they continue moving apart, their mutual gravitational attraction gradually slowing them down. Eventually, they stop, turn around, and fall back toward each other for another passage. This process repeats multiple times, with each passage bringing the galactic cores closer together. But what causes the cores to eventually merge rather than oscillating forever? The answer is dynamical friction, a gravitational drag force that causes massive objects moving through a sea of smaller objects to lose energy. When a massive object like a galactic core moves through a field of stars and dark matter, its gravity attracts surrounding material, creating a wake of higher density behind it. This gravitational wake pulls backward on the massive object, slowing it down. The energy lost by the moving object is transferred to the surrounding material, which is scattered into higher energy orbits. Through dynamical friction, the cores of two merging galaxies gradually lose orbital energy after each passage, causing them to fall deeper into their mutual gravitational potential. The oscillations become smaller with each cycle, and eventually, the cores merge into a single combined structure. This process can take hundreds of millions to billions of years, depending on the masses involved and the initial orbital parameters. How do astronomers predict and visualize such complex gravitational interactions? The primary tool is computer simulation, specifically a technique called n-body simulation. In an n-body simulation, the galaxy is represented as a collection of particles, each one representing a clump of stars, gas, or dark matter. The simulation calculates the gravitational force on each particle from all other particles, then moves each particle according to Newton's laws of motion. By repeating this process for millions of small time steps, the simulation traces the evolution of the system over billions of simulated years. Early galaxy merger simulations in the 1970s and 80s used only a few thousand particles, severely limiting their ability to capture the complex dynamics of real galaxies. Modern simulations can employ billions of particles, resolving structures within galaxies in exquisite detail. These simulations have revealed the full richness of galaxy merger dynamics, showing how tidal tails form and evolve, how starbursts are triggered, how supermassive black holes spiral toward the center, and how the final merged galaxy settles into equilibrium. The simulations also reveal the inherent unpredictability of galaxy mergers. Small changes in initial conditions, the exact angle of approach, the precise velocities involved. The detailed distribution of dark matter can lead to significantly different outcomes. This sensitivity to initial conditions is characteristic of chaotic systems and explains why astronomers express predictions about the Milky Way-Andromeda merger in terms of probabilities rather than certainties. We cannot precisely predict which stars will end up where because the system is fundamentally chaotic over the timescales involved. The physics of galaxy collisions is thus a story of gravitational interactions, playing out across vast scales of space and time. Stars pass through stars without touching, yet gravity scrambles their orderly motions into random chaos. Gas clouds collide directly, triggering new star formation. Dark matter halos merge smoothly, reshaping the gravitational landscape. Dynamical friction drains energy from the system, drawing the galactic cores inexorably together. And through it all, the patient mathematics of n-body simulation allows us to watch, in compressed time, the slow ballet of cosmic transformation that will unfold over billions of years. Having explored the physics that governs galaxy collisions, let us now trace the actual sequence of events that will unfold as the Milky Way and Andromeda come together. This timeline spans billions of years and involves transformations so gradual that no human lifetime could perceive them, yet so profound that they will fundamentally reshape our galaxy and the night sky visible from any surviving worlds. We will walk through this cosmic calendar stage by stage, imagining what observers might witness at each major milestone if they could somehow be present to see it. Today, in the present era, Andromeda appears as a faint smudge in the constellation that bears its name, visible to the naked eye from dark locations as a fuzzy patch roughly 6 times the apparent width of the full moon, though most of that extent is too dim to see without optical aid. Only the bright central core is visible to unaided human eyes. The galaxy lies approximately 2.5 million light-years away, far beyond any plausible reach of human technology for the foreseeable future. The photons striking your eye when you observe Andromeda departed that galaxy during the Pliocene epoch on Earth, when our ancestors were still mastering the use of stone tools. For the next 2 billion years, remarkably little will change from a human perspective. Andromeda will grow slowly larger and brighter in the night sky as the separation between our galaxies decreases. But the change will be so gradual that no human civilization, even one lasting thousands of years, would notice the difference without precise astronomical instruments. The approach velocity of roughly 110 kilometers per second sounds impressive, but across distances measured in millions of light years, it produces only glacially slow apparent change. Andromeda will roughly double in apparent size over this 2 billion year span, growing from a subtle smudge to a more prominent fuzzy patch, but still appearing as a distant object rather than a galactic companion, as the galaxies swing out to their maximum post-passage distance. During this separation phase, the night sky would remain spectacular, but would evolve as the geometry changes, fading away. Approximately 5 billion years from now, give or take several hundred million years depending on the exact dynamics, the galaxies reach their maximum separation and begin falling back toward each other. The second passage follows, bringing the galactic cores closer together than the first encounter. This second passage is even more disruptive than the first, with tidal forces reaching deeper into both galaxies and disturbing regions that survived the initial encounter relatively intact. At 5.1 billion years, according to some simulations, the two galactic cores appear as a close pair of bright lobes in the sky, separated by a relatively narrow gap, but surrounded by a chaotic swirl of disrupted stellar streams. The organized spiral structure of both original galaxies would be essentially destroyed by this point, replaced by irregular distributions of stars, gas, and dust. Star formation would surge again as additional gas clouds collide, creating a second major starburst episode. After the second passage, the pattern repeats but with diminishing amplitude. Each subsequent passage brings the cores closer together as dynamical friction drains energy from their orbital motion. The oscillations become smaller and faster, like a pendulum slowly coming to rest. Throughout this settling phase, which spans roughly 1 billion years, the night sky would present a constantly evolving spectacle as the two galactic cores spiral toward their final union. By approximately 6 to 7 billion years from now, the merger is essentially complete. The two galactic cores have merged into a single structure, their supermassive black holes having either already combined or orbiting each other at close range as they spiral toward their own union. The tidal tails have begun to fall back, reincorporating their stars into the main body of the merged galaxy. The violent episodes of star formation have largely subsided as the available gas is consumed or expelled. The resulting galaxy bears no resemblance to either of its spiral progenitors. Gone are the elegant disk structures with their organized rotation and sweeping spiral arms. In their place stands a giant elliptical galaxy, a roughly spherical or football-shaped collection of stars moving in random orbits around a common center of mass. This new galaxy, sometimes called Milkomeda or Milkdromeda in popular accounts, contains more than 1 trillion stars, the combined populations of both parent galaxies, plus any new stars created during the merger. The night sky from within Milkomeda would look quite different from what we see today. Without the flattened disk structure of a spiral galaxy, there would be no Milky Way band stretching across the heavens. Instead, the sky would be filled with a more uniform distribution of stars, though with higher density toward the galactic center. The bright core of the elliptical galaxy would dominate one region of the sky, a concentrated glow from the dense central stellar population surrounding the merged supermassive black hole. Throughout this entire timeline, what happens to our solar system? This question is difficult to answer with certainty because individual stellar trajectories are highly sensitive to the details of the gravitational interactions encountered. Simulations that track particles with orbits similar to the Sun's show a range of possible outcomes. In most scenarios, the solar system is flung outward from its current position, ending up in the outer regions of the merged galaxy at distances of perhaps 50,000 to 100,000 light-years from the center, roughly 2 to 4 times farther from the galactic center than our current location of 26,000 light-years. Some simulations show more dramatic possibilities. In roughly 12% of cases, according to early estimates, the solar system might be ejected from the merging system entirely during the gravitational chaos, sent wandering into intergalactic space as a rogue star system. This would be lonely but not necessarily catastrophic. The sun would continue to shine, and the planets would continue in their orbits, merely lacking a galactic home. In other scenarios, the solar system might be captured by Andromeda before the final merger, ending up as a temporarily Andromedan star before the two galaxies fully combine. There is also a small probability that gravitational encounters during the merger could disturb the solar system itself. A close passage by another star might perturb the Oort cloud, the distant shell of comets surrounding our system, potentially sending a shower of comets into the inner solar system. This could increase the rate of impacts on any surviving planets. However, such close passages remain unlikely even during the gravitational chaos of the merger, and most simulations suggest the inner solar system would remain intact. Of course, none of these considerations about the solar system's fate will matter to Earth. Long before the Milky Way-Andromeda merger reaches its dramatic phases, our planet will have become uninhabitable. The sun is gradually brightening as it ages, and within roughly 1 to 2 billion years, this increased luminosity will raise Earth's temperature beyond the point where liquid water can exist on the surface. By the time the merger begins in earnest, Earth will be a scorched, lifeless world, and the sun itself will be approaching the end of its main sequence lifetime, eventually expanding into a red giant and engulfing the inner planets. Any observers witnessing the spectacular night sky of the merger will not be standing on Earth. They might be the descendants of humanity if we have colonized other worlds or constructed space habitats in the outer solar system. They might be entirely different intelligent species that arise elsewhere in one or both galaxies. Or there might be no observers at all, the light show playing out for an empty cosmic auditorium. The merger will happen regardless, indifferent to whether anyone watches. Among the most dramatic consequences of galaxy collisions is the phenomenon astronomers call a starburst, a period of extraordinarily intense star formation that can transform a galaxy's stellar population within a cosmically brief span of time. When the Milky Way and Andromeda finally merge, this stellar firestorm will almost certainly ignite, creating vast numbers of new stars in brilliant nurseries scattered throughout the combined system. Understanding starbursts helps us appreciate not just the violence of galaxy collisions, but also their creative power, their ability to generate new stellar generations that would never have formed in isolated quiescent galaxies. In a normal spiral galaxy like the Milky Way, star formation proceeds at a relatively modest pace. Our galaxy converts roughly 1 to 3 solar masses of gas into new stars each year, a rate that has remained fairly steady for billions of years. This gentle, ongoing process creates the mix of stellar ages we observe, with ancient stars in the central bulge and halo coexisting with young stars in the spiral arms, where gas clouds are currently collapsing. At this rate, the Milky Way will continue forming stars for many billions of years, gradually consuming its reservoir of gas until too little remains to sustain further stellar creation. A starburst represents a dramatic acceleration of this process, sometimes by factors of 10, 50, or even 100. Instead of forming a few solar masses of new stars per year, a starburst galaxy might form hundreds or even thousands of solar masses worth of stars annually. This prodigious rate of stellar creation cannot be sustained indefinitely. The gas supply is consumed too rapidly, and the intense radiation from massive young stars heats and disperses the remaining gas, eventually shutting down the burst. Typical starbursts last somewhere between 100 million and 500 million years. A brief episode by cosmic standards, but long enough to fundamentally alter a galaxy's stellar demographics. What triggers starbursts? The answer, in most cases, is galaxy interactions and mergers. When two galaxies approach and interpenetrate, their interstellar gas, which fills the space between stars and diffuse clouds, experiences direct collisions. Unlike stars, which pass through each other without touching due to their enormous separations, gas clouds are sufficiently extended and diffuse that they actually collide when galaxies merge. These collisions comprise of our local merger. Beyond the gravitational waves, the black hole merger may produce electromagnetic fireworks as well. If significant gas remains in the nuclear region of the merged galaxy, material will fall toward the black holes and form an accretion disk, a swirling disk of superheated matter spiraling inward toward the event horizon. Accretion disks around supermassive black holes can be extraordinarily luminous, outshining all the stars in their host galaxies combined. Such actively accreting supermassive black holes are known as active galactic nuclei, with the most luminous examples called quasars. During certain phases of the black hole merger, particularly if gas is funneled toward the center by the gravitational chaos of the galaxy merger, one or both black holes might accrete enough material to power a brief quasar phase. The central region of the merged galaxy would blaze with light across the electromagnetic spectrum, from radio waves through visible light to X-rays and gamma rays. Any observers in the outer regions of the galaxy would see their night sky dominated by a brilliant point of light at the galactic center, far outshining all other celestial objects. Whether a quasar actually forms depends on whether sufficient gas is available. By the time the black holes finally merge, perhaps several 100 million years after the galaxies complete their union, much of the gas in the central region may have been consumed by star formation or expelled by previous episodes of activity. Predictions about quasar formation during the Milky Way-Andromeda merger remain uncertain. Some simulations suggest a bright quasar phase is likely, while others indicate the event may be relatively quiet electromagnetically, with the gravitational waves being the primary observable signature. One final consideration is the gravitational wave recoil or kick that can occur during black hole mergers. When two black holes with different masses or different spins merge, the gravitational waves are emitted asymmetrically, carrying momentum away from the system in a preferred direction. By conservation of momentum, the merged black hole receives a kick in the opposite direction. For certain spin configurations, this kick can be quite large, reaching velocities of thousands of kilometers per second. If the Milky Way-Andromeda black hole merger produces a strong kick, the merged black hole could be ejected from the galactic center, wandering through the galaxy for millions of years before dynamical friction brings it back to rest. In extreme cases, the kick velocity might exceed the escape velocity of the galaxy, sending the merged black hole out into intergalactic space forever. This would leave the merged galaxy temporarily without a central supermassive black hole, a highly unusual situation. More likely, the kick velocity will be modest enough that the merged black hole remains bound to the galaxy, oscillating about the center until it settles down. But for a brief period after the merger, the central region of Andromeda might appear. Perturbations from passing stars can alter their orbits, potentially sending some of them plunging into the inner solar system. During the merger, when the density of nearby stars temporarily increases and closed passages become more common, the rate of Oort cloud perturbations would rise substantially. This could trigger what astronomers call a comet shower, a period of elevated comet activity in the inner solar system as disturbed Oort cloud objects fall inward toward the Sun. Comet showers increase the probability of impacts on planets, including any planets that might harbor life. The Earth has experienced major impacts throughout its history, most famously the asteroid impact 66 million years ago that contributed to the extinction of the dinosaurs. An increased rate of comet impacts during the galactic merger could trigger additional mass extinctions or fundamentally alter conditions on any inhabited worlds. This represents perhaps the most direct threat the merger poses to life, not the grand galactic collision itself, but the local consequences of gravitationally disturbed comets. However, all of these considerations about the solar system's fate during the merger must be placed in a broader context. Long before the Milky Way and Andromeda come together, long before any of these gravitational disruptions occur, the Earth will have become uninhabitable through an entirely different process, the natural evolution of the Sun. Stars do not shine forever. They are powered by nuclear fusion in their cores, converting hydrogen into helium and releasing energy in the process. This process cannot continue indefinitely. Eventually, the hydrogen fuel runs low and the star must change. Our Sun is currently about 4.5 billion years old, roughly halfway through its main sequence lifetime. In another 5 billion years or so, it will exhaust the hydrogen in its core and begin the transformation into a red giant. But the Sun does not need to become a red giant to galaxy, a roughly spheroidal or football-shaped collection of stars without any significant disk component or spiral arms. Elliptical galaxies are common in the universe, particularly in dense galaxy clusters where mergers occur frequently. They range in size from dwarf ellipticals containing only millions of stars to giant ellipticals containing trillions, the largest galaxies known. Milky-Way will fall somewhere in the middle of this range, a moderately large elliptical galaxy containing the combined stellar populations of its two spiral progenitors. The transformation from spiral to elliptical occurs through the gravitational randomization of stellar orbits that we discussed earlier. In a spiral galaxy, stars move in relatively orderly fashion, orbiting the galactic center in roughly circular paths that all lie approximately in the same plane. This coordinated motion is what creates the flat disk structure and allows spiral density waves to propagate, generating the familiar spiral arm pattern. When two spirals merge, gravitational scattering destroys this coordination. Stars are kicked into new orbits oriented in random directions, some highly elliptical, some more circular, but no longer confined to a common plane. The result is a puffy three-dimensional distribution of stars rather than a thin disk. Some simulations have suggested the possibility that Milky-Way might retain some disk-like structure, perhaps forming what astronomers call a superspiral rather than a pure elliptical. This outcome depends on the details of the merger, particularly the relative orientations of the two galactic disks and the amount of gas that survives to form new stars after the collision. If significant gas remains and the angular momentum of the combined system is preserved, a new disk might gradually form from this gas, potentially recreating spiral structure on very long timescales. However, most simulations favor the elliptical outcome, with the majority of the gas being consumed during merger-induced starbursts or expelled by supernova-driven galactic winds. The stellar population of Milky-Way will reflect its merger origin. It will contain stars from both the Milky Way and Andromeda, their original galactic affiliations no longer distinguishable once they are mixed together within the common gravitational potential. The total number of stars will exceed 1 trillion, the sum of both parent populations, plus whatever new stars are created during the merger-induced starburst. This makes Milky-Way a substantial galaxy, larger than most spirals, but not among the true giants of the elliptical class. The age distribution of stars in Milky-Way will be complex. Both parent galaxies contain stars spanning a wide range of ages, from ancient population members formed in the early universe to young stars born within the last few million years. The starburst triggered by the merger will add a new cohort of stars, all born within a relatively narrow window of time centered on the merger epoch. These starburst stars will initially be bright and blue, dominated by massive, hot, short-lived stars. But within a few 100 million years, the massive stars will have died, and the starburst cohort will fade to become a population of lower-mass, longer-lived stars indistinguishable in many ways from the older stellar populations. At the center of Milky-Way will sit the merged supermassive black hole, formed from the coalescence of Sagittarius A star and Andromeda's larger central black hole. With a combined mass of roughly 100 to 150 million solar masses, this black hole will anchor the gravitational center of the new galaxy, holding the dense central stellar population in its vicinity. For a time after the merger, this black hole might be actively feeding, consuming gas funneled toward the center during the collision and shining as a bright active galactic nucleus. But eventually, the fuel supply will dwindle and the black hole will return to quiescence, a dark, gravitational presence at the heart of an otherwise normal elliptical galaxy. The stellar dynamics of Milky-Way will differ substantially from what we experience in the Milky Way. In our current spiral galaxy, stars orbit the galactic center in roughly the same direction, all participating in the organized rotation of the disk. In Milky-Way, stars will orbit in all directions, their trajectories reflecting the randomized outcome of the merger process. A star in Milky-Way might find itself moving inward while its neighbor moves outward, or moving north while another moves south. The galaxy will be supported against gravitational collapse not by organized rotation, but by the random motions of its constituent stars, a state astronomers call velocity dispersion support. This difference in dynamics has implications for any civilizations that might exist within Milky-Way. In a spiral galaxy, neighboring stars tend to move together, maintaining their relative positions over long periods as they all orbit the galactic center. In an elliptical galaxy, stars on very different orbits can pass relatively close to each other, creating a more dynamically active stellar environment. The probability of close stellar encounters, while still very low, is somewhat higher in elliptical galaxies than in spiral disks. This could affect long-term planetary system stability and the rate of Oort cloud perturbations over billions of years. Star formation in Milky-Way will decline dramatically after the merger-induced starburst subsides. Elliptical galaxies are typically poor in cold gas, the raw material from which stars form. The merger will consume much of the available gas through the starburst and expel much of the remainder through supernova-driven outflows. What remains will settle toward the center of the galaxy, where it might support low levels of ongoing star formation, but nothing comparable to the vigorous star creation currently occurring in the Milky Way's spiral arms. This lack of star formation means that Milky-Way will gradually age, its stellar population becoming older and redder as massive blue short-lived stars die off without replacement. Over tens of billions of years, the galaxy will transition from a mixture of stellar ages to a population dominated by ancient, low-mass red dwarfs and stellar remnants. The night sky from within Milky-Way will gradually darken as fewer and fewer bright stars remain to illuminate it. The long-term evolution of Milky-Way extends far beyond the timescales we have discussed so far. Elliptical galaxies are essentially stellar graveyards, slowly fading as their stars burn out one by one. The low-mass red dwarf stars that constitute the majority of any stellar population can burn for trillions of years, far longer than the current age of the universe. The very last stars in Milky-Way might not die until the universe is 100 times older than it is today, their feeble red light the only illumination in an otherwise dark cosmos. Before that final fading, Milky-Way may experience additional mergers. The local group contains other galaxies that will eventually fall into the combined system, including the Triangulum galaxy and the various dwarf satellites of both parent spirals. Each merger will add more stars to Milky-Way, potentially triggering additional starbursts if sufficient gas accompanies the incoming galaxy. Over billions of years, Milky-Way might grow substantially, absorbing its entire local group neighborhood into a single massive elliptical. Eventually, Milky-Way will stand alone. The accelerating expansion of the universe is carrying other galaxies away from us at ever-increasing speeds. Distant galaxies are already receding faster than light, carried by the expansion of space itself, and will eventually pass beyond our cosmic horizon, their light forever unable to reach us. Over tens of billions of years, the observable universe will shrink until only the gravitationally bound local group remains visible. Milky-Way and its absorbed satellites will constitute an isolated island of matter in an otherwise empty dark universe, cut off from the rest of cosmic history. Future astronomers in Milky-Way, if any exist, will face a profound challenge, looking outward, They will see nothing but darkness, no other galaxies, no evidence of the larger cosmic structure that we can currently observe. They might conclude that their galaxy constitutes the entire universe, a single island of stars in an infinite void. The cosmic microwave background, the ancient light from the Big Bang that tells us so much about the universe's origin, will have redshifted beyond detectability. The evidence for cosmic expansion, for the Big Bang itself, will have disappeared, erased by the very expansion it represents. This isolation represents the ultimate fate of all gravitationally bound structures in an accelerating universe. Every galaxy group and cluster will eventually stand alone, its neighbors carried beyond the horizon by cosmic expansion. Milky-Way is our future home, but it is also our future prison, a finite collection of matter isolated in an infinite expanding void. The story of the Milky Way-Andromeda merger is ultimately a story about the transition from connection to isolation, from a universe rich in observable neighbors to a universe containing only the single merged remnant of our local cosmic family. Our predictions about what will happen when the Milky Way and Andromeda merge are not merely theoretical speculations. They are grounded in observations of countless other galaxy collisions occurring throughout the universe right now. By studying these cosmic train wrecks at various stages of their evolution, astronomers have assembled a detailed understanding of how mergers unfold, what structures they create, and what effects they have on the galaxies involved. These ongoing collisions serve as natural laboratories, testing our theories and refining our predictions about our own galactic future. The most famous example of a galaxy collision in progress is the antennae galaxies, a pair of interacting spirals located roughly 60 to 70 million light-years away in the constellation Corvus. Their distinctive name comes from the two long, curved tidal tails extending outward from the merger, which in early photographs resembled the antennae of an insect. These tails span an astonishing distance, stretching for nearly 500,000 light-years from tip to tip, far exceeding the original size of either parent galaxy. The antennae began their interaction roughly 600 to 900 million years ago, when the two spiral galaxies first passed close enough to begin affecting each other gravitationally. What we see today represents an intermediate stage of the merger, after the initial close passages have disrupted both galaxies, but before the final coalescence has occurred. The two galactic cores remain distinct, visible as bright concentrations of stars separated by roughly 30,000 light-years. But the original spiral structures have been destroyed, replaced by chaotic distributions of stars, gas, and dust. What makes the antennae particularly valuable for understanding galaxy mergers is the extraordinary burst of star formation occurring throughout the interaction region. Hubble Space Telescope observations have revealed over 1,000 young star clusters concentrated in the overlap zone where the two galaxies have interpenetrated. These clusters are massive, each containing hundreds of thousands or millions of stars. And they are young, most having formed within the last few hundred million years in response to the collision. The rate of star formation in the antennae exceeds that of normal spiral galaxies by factors of 10 to 20, demonstrating the starburst phenomenon in spectacular fashion. The antennae provide a preview of what the Milky Way and Andromeda might look like during certain phases of their merger. The long tidal tails, the disrupted spiral structure, the intense central starburst, these are features we expect to see in our own galaxy's future, playing out over similar timescales. Of course, every merger is different depending on the specific masses, orientations, and orbital parameters involved. But the basic physics is the same, and the antennae demonstrate what that physics produces in the real universe. Another instructive example is Stephan's quintet, a visual grouping of 5 galaxies in the constellation Pegasus. 4 of these galaxies, designated NGC 7377, NGC 7380, NGC 7380b, and NGC 7319, are physically associated and in the process of interacting. The 5th, NGC 7320, is actually a foreground galaxy that happens to lie along the same line of sight, but is not involved in the collision. This coincidence of projection makes Stephan's quintet appear more crowded than it actually is, But the true interacting quartet remains a fascinating example of multi-galaxy dynamics. The galaxies in Stephan's quintet have been interacting for hundreds of millions of years, and the signs of this interaction are everywhere visible. Tidal tails extend from multiple members. Gas has been stripped from the galaxies and now fills the intergalactic space between them, and one member, NGC 73UMRB, is currently plowing through this intergalactic medium at high speed, generating shock waves visible in X-ray observations. The complex gravitational dynamics of this multi-galaxy interaction illustrate the challenges of predicting merger outcomes when more than two galaxies are involved. Stephan's quintet is relevant to our own future because the local group contains more than just the Milky Way and Andromeda. The Triangulum Galaxy, the large and small Magellanic Clouds, and numerous smaller dwarf galaxies will all participate in the eventual consolidation of our cosmic neighborhood. The gravitational interactions among these multiple bodies make precise predictions difficult. Just as the interactions within Stephan's quintet create complex time-varying dynamics that are challenging to model. Beyond these specific examples, astronomers have cataloged thousands of interacting and merging galaxy pairs throughout the observable universe. The ARP catalog, compiled by astronomer Halton Arp in the 1960s, documented hundreds of peculiar galaxies, many of which turned out to be mergers in progress. Burn through their nuclear fuel and die. The universe expands, carrying galaxies apart and reshaping the cosmic landscape. What we see when we look at the night sky is a snapshot of an ongoing process, a still frame from a movie that has been playing for nearly 14 billion years and will continue for at least as long into the future. The Milky Way-Andromeda merger is one chapter in this ongoing cosmic evolution. It is not an anomaly or a disaster, but a normal process, the kind of gravitational interaction that has shaped galaxies throughout the history of the universe. The spiral galaxies we see today were themselves built through countless smaller mergers over cosmic time. The elliptical galaxy that will emerge from the Milky Way-Andromeda collision is not an ending, but a transformation, a new configuration of ancient matter that will itself evolve over the eons to come. The fourth lesson concerns our cosmic isolation. The merger of the Milky Way and Andromeda is not merely a local event. It is part of the larger consolidation of the local group into a single gravitationally bound system. As this consolidation proceeds and the universe continues to expand at an accelerating rate, our cosmic neighborhood will become increasingly isolated. Distant galaxies are already being carried away from us by the expansion of space, and this expansion is accelerating, meaning that more and more galaxies are passing beyond our cosmic horizon every year. Eventually, perhaps hundreds of billions of years from now, the only matter accessible to any observer in our region will be the merged remnant of the local group, an island of stars in an otherwise empty, dark universe. This future isolation represents one of the most profound implications of modern cosmology. We live in a privileged moment when the universe is young enough that we can still see evidence of its origin and structure. We can observe distant galaxies, measure their motions, and infer the expansion of space. We can detect the cosmic microwave background, the ancient light from the epoch when the universe first became transparent. We can piece together the history of cosmic evolution from Big Bang to present. Future observers, billions of years hence, may lack access to this evidence. The expansion of space will have erased it, carrying the cosmic microwave background beyond detectability and removing distant galaxies from the observable universe entirely. The fifth and final lesson is perhaps the most personal. When we contemplate the merger of two galaxies over timescales of billions of years, we are engaging in an act of imagination that connects us to something far larger than ourselves. We are acknowledging our place in a universe of staggering scale and duration, a universe that operated according to its own physical laws for billions of years before we arrived and will continue to do so for billions of years after we are gone. This acknowledgement is not a diminishment of human value, but an expansion of human context, a recognition that we are participants in a cosmic story whose full scope exceeds any individual comprehension. The story of the Milky Way and Andromeda is ultimately a story about connection and transformation. Two island universes, separated by millions of light years but bound by gravity, are falling toward each other across the cosmic void. When they meet, they will not destroy each other. They will transform each other, creating something new from the combination of what each one was. Stars will be scattered, black holes will merge, new generations of stars will be born in the fires of collision, and a new galaxy will emerge, different from either parent but containing the heritage of both. Whether anyone will be present to witness this transformation is unknown. Perhaps humanity will have spread across the stars by then, adapting to new worlds and new circumstances, surviving the death of our sun and the transformation of our galaxy. Perhaps other intelligent species will arise in our galaxy or in Andromeda to observe and understand the merger as it unfolds. Perhaps no observers will exist at all, the cosmic drama playing out for an empty auditorium. The universe does not require an audience. It will proceed regardless of whether anyone is watching. But today, here, now, we are watching. We are the universe become aware of itself, matter organized in patterns complex enough to contemplate its own origin and fate. We can look up at that faint smudge in the constellation Andromeda and understand what it is, how far away it is, how fast it is approaching, and what will happen when it arrives. This understanding is itself a kind of participation in the cosmic story, a way of being present to events we will never directly experience. The Milky Way-Andromeda merger lies billions of years in the future, beyond any reasonable horizon of human planning or concern. But thinking about it, learning about it, imagining what it will be like, these activities enrich our present moment. They expand our sense of what is possible, deepen our appreciation for the universe's grandeur, and remind us that we are part of something far larger than ourselves. As you go about your daily life, remember that the faint smudge of Andromeda is up there in the autumn sky, visible on clear dark nights, slowly but inexorably approaching. Remember that every photon of light from that distant galaxy has traveled for 2.5 million years to reach your eye, carrying information about 1 trillion suns in a cosmic companion we are destined, one way or another, to meet. Remember that the universe is not static, but evolving, not finished, but still unfolding, not separate from us, but the very context of our existence. And if you found this journey through cosmic time and space engaging, if it sparked your curiosity or expanded your perspective, consider subscribing to this channel and exploring more of the universe with us. There are countless more stories to tell about the cosmos, countless more wonders to explore, and we would be honored to share them with you. Until next time, keep looking up, keep wondering, and remember that we are all made of star stuff, contemplating the stars from which we came and to which we will one day return. Thank you for watching Deep Calm Science. If you enjoyed this exploration of the Milky Way-Andromeda collision, please like this video and subscribe to our channel for more calm, thoughtful explorations of the universe and our place within it.